So here's an example where we must use Kirchhoffs rules, or Kirchhoffs laws as they are called, to find the current through each resistor and the charge on the capacitor in this situation. Whenever you have power supplies that are not just in series, when they're in series it's easy, just add the potentials across each one. But in this case, they're not just in series. There's a lot of complicated interaction here. So we must use, for this problem, we got to use Kirchhoffs rules. If at all possible, you want to use reduction because it's just a lot simpler, as you will see. So the first thing to do is to label all the possible junctions here. I've labeled them A, B, C, D, E, F, G, H, as you can see right here. And what we're going to do is we're just going to pick one of the junctions. Let's just pick junction C here, and we'll just label some currents that are going in and out of junction C. Now, we could be totally wrong on these. I'm just going to take just a wild guess. I'm going to say I1, let's say label it I1, going up right there into C. Now, if I'm wrong about the direction of I1, when I solve for the I1, it'll come out negative. It's not a problem. So that's I1. Let's go ahead and label this one. Let's assume it's going that way and call it I2. If we're wrong about the direction, that's okay. Now, if these are both going in, I got to have one that's going out right there, which I'm going to call I3. Using the junction rule at C, I1 and I2, the presumed direction of currents, are going into junction C. I3 is going out of junction C, so that means that I1 plus I2 equals I3. All right, I've got one equation, but there's three unknowns. How many more equations am I going to need? At least two more. Why don't I just do a loop rule for C, D, E, F? Loop rule for C, D, E, F. And C, D, E, F, I should say C. It won't work unless it's all the way around back to here. So to do this, again, you take a walk around. When you walk around, you don't have to walk around in the direction of current. Now, I'm going to in this case, but I don't have to. So I'm just going to take a walk around here. Here's my footsteps here. I'm going that way. And notice that if I'm going that way, there's my direction of my travel like that. I'm going in the direction of my presumed current. So that will mean that from there to there, it's negative I3 R3 is my first term. Why is it negative? Because I'm starting at high potential and it drops down to low potential because it's going in the direction of presumed current. Then I'm going to keep traveling around like this way, and now I've got to go across this electric EMF source here. And I'm starting here, and again, the short side is the negative side, long side is the positive side. Am I going to a higher potential, or am I going to a lower potential as I go across that? I'm going uphill, so it'll be plus 4 volts. I'm just going to use the number there, plus 4 from there to there. Keep going around here. No potential changes there. Keep going here. Now, this is where I'm going through here, again in the direction of presumed current. So I'm starting there, ending there. I'm assuming I'm going downhill. It's going in the direction of current. So that'll be minus I2 times R2. And that's going to equal to 0. I'm going to actually plug in my numbers here. All right, so now I've got 2 equations, but still 3 unknowns. Notice that in this equation right here, I've got I3 and I've got I2. So my next equation must have I1 in it. So what I'm going to do, because I need I1 right here, where else can I find I1? Well, as we can figure out conceptually right here, let's check this out. What's the current through this resistor R1? Well, here's a conceptual way of looking at that. What's the current through this capacitor right here? Assuming this is at steady state, there is no current going through that. It's kind of like it's just like a closed door. Nothing can get through there. So that means that the current right here, this is 0. There can be no current right here. This is 0. So what's the current right there through this R1? Well, notice that I1's coming out of B, and there's no other place that I1's going, so this must also be I1, because there's no current there, into junction B. It's got to add up to I1. This is 0. That's got to be I1. That means I1's got to be right there, which means that this also has to be I1. So this means that if I do this loop right here, that will allow me another equation that's got I1 in it. So I know I1 is right there. Let's go ahead and do this loop. We're going to do the loop rule for this loop. C, F, G, B, C. Again, starting and ending at the same point. So starting at C, now if I travel around, and again my direction of travel, I'm walking around this way, that's my traveling direction. Notice I'm going in the opposite direction of the presumed current I2. So that means what I'm going to have is, in the opposite direction will be plus I2 R2, and because I'm starting at this end and going to that end, that is like going uphill. So I'm going from after it's gotten through the resistor to before it's gotten through the resistor. So that's going to be going to a higher potential. And then I continue on here, and then going down this way in the direction of presumed current, it'll be minus I1 R1. And then keeping going around, and this is the direction of travel is this way, that away. And notice I'm going from the negative end to the positive end of this thing. So I'm going uphill as I travel around that way. So that'll be plus 8 volts. And then I'm from here to there, there's no resistor, so I'm back where I started. So that all adds up to 0. So I'm going to put in the numbers here now, equals 0. So here's my final equation. Now I've got 3 equations with 3 unknowns. I'm actually not going to solve these equations. You probably won't have to solve 3 equations with 3 unknowns on the AP exam just because it takes so long. More than likely, if they have a problem like this, they'll ask you to set up the equations, or it'll be much simpler. What I do want to do, however, I want to show you how to find the charge on this capacitor right here. I'm going to use the loop rule for the loop BGHA. Back to B. Always got to start and end at the same spot. Now going in this direction of travel like that, notice that's going opposite the polarity. I'm going from high potential to low potential. It's like going downhill. So that'll be minus 8 volts. Minus 8. Keep going down. Okay, now I've got to figure out, well, what's going on here? I do not know which direction the polarity is of this capacitor. So let's just take a look here and see if we can figure it out. Well, I'm going to make an assumption. This is the positive end of my battery, so I'm going to assume that this end is positive right there and that this end is negative. So as I continue around my circle right here, and I was going in this direction right here, going this way, I'm going from negative to positive, so as I travel around that way, I'm going to a higher potential. So that'll be plus the delta V across the capacitor. That is Q over C. And then I'm going to keep going, and notice that when I get here, I am going downhill again. So it'll be minus 3. And then I'm all the way back to where I started. So that adds up to 0. So in other words, I've got, when I put Q over C on one side and the rest on the other side, Q over C is 11 volts, and that means that Q over 6 microfarads equals 11 volts. So the charge on the capacitor is 66 times 10 to the negative 6 coulombs. But again, if there's any way to avoid this, you're going to want to use reduction because it is much, much easier. It takes a lot less time.